Right? Good morning, students. So last week we started a topic called atoms, right? Atomic physics. A quick revision, then we'll go into the topic. Okay. So atomic physics, the first topic. So who started that? So Dalton. So we discussed all the things. Just a quick revision. See the things, right? So Dalton, what he said? So matter is made up of atoms, and it is the smallest unit. Atom is the smallest unit, he said. That is the disadvantage already we studied, right? So matter is made up of atoms. It is the smallest unit. But atom is the smallest unit. Still further we have to go inside. Still further we have to go inside of the atom, right? So this is the failure of the Dalton's theory. Next, who took up that project? Thomson, right? So he made some changes here, and what he said, atom, inside the atom, so atom is neutral, and inside the matter is positive, and electrons will be there like the seeds in the watermelon, all those things he said in the plum pudding model. And later on he gave an experiment on the specific charge per unit mass. That experiment we have seen, right? So next, after this, he forgot in the sense he gave electron is negative charge, right? But what is the value of that? What is the magnitude of that? He didn't give, right? So what is the magnitude of that? He didn't give. So how we can determine the magnitude of the charge? By using this oil drop experiment. That also we have seen. Yes or no? So oil drop experiment. So with this, in this experiment, we can determine what? The magnitude of charge. We can determine the magnitude of what? The magnitude of charge. Right? All these experiments we have seen. Specific charge we have seen. An oil drop experiment we have seen. Try to see the videos if you have any doubts there. Okay. So next, who took up this project? Rutherford. And what he said, what is the disadvantages here in the J.J. method? So he said, atom is neutral, but electrons will be fixed places. Electrons will be in the atom, which is fixed. But that is not absolutely correct, right? So this project again took up by the Rutherford. Project took up by who? Took up by the Rutherford. And he did some experiments. That experiment is nothing but alpha scattering experiment, right? So try to see the angles. These are the exact angles, right? So in that class, what you have seen that according to the experiment I said, but according to the values, you have to remember these values. Try to remember this. Okay. So alpha scattering experiment, what it is? Alpha particles will move with the high energy, and the gold foil will be there, which is very thin. So which is made up of only one atom of one layer of the atoms, gold atoms, right? So alpha particles and how it is deviated and all. He said in his experiment called alpha scattering experiment, right? So most of the alpha particles in that experiment went undeviated, which is less than 1 degree. Went undeviated, very less. 1 degree in the sense very less, right? So almost we can tell it is undeviated. So the angle is less than 1 degree. Next, the same. Next, 0.14% is in that which is deviated, which is greater than 1. Already the discussion done. So try to remember these angles. Most of the alpha particles went undeviated, which is less than 1 degree. Almost undeviated, less than 1 degree. So next, 0.14% is deviated, greater than 1 degree. Just it is deviated. Next, 1/8000 number of alpha particles deviated greater than 90 degrees. Greater than 90 degrees out of what? 8,000 alpha particles in that ratio. Okay, not exactly 1. That ratio is like that. Okay, which is greater than 90 degrees. Next, 1 in 10 to the power 6 deviated 180 degrees. In a sense, retraces back. So graph. So for example, if theta is 0 or very less, then what will happen to the number of alpha particles, which is deviated very less? Which is deviated very less. Next, angle increasing, so number of particles deviating also increases. See? Theta less than 1. Next, greater than 1, very less. And greater than 90 degrees, very less. See, greater than 90 degrees, you can see somewhere around here. Very less, right? So if it is 180 degrees, still very less. So you can decrease this further. See, this decrease. So this is the graph of number of particles and the scattering angle. So number of particles. So how much it is deviating by this angle will be very less. See, if angle increases, number of alpha particles deviating will be very less. So we can draw the curve like that. So clear about these points, right? So already we discussed all these things. Just a quick revision we have seen. So these angles, try to remember, very important. You have to write in the exams, not like only the experiment. You have to write in theoretical way, right? Important question, I think, for board exams is Rutherford alpha ray scattering experiment. Next, we'll go into the topic. After this alpha ray scattering experiment, what we studied? We continued the Rutherford's thesis, right? So what we studied later on, we studied about the distance of the closest approach, energy conservation we have written, and later on we discussed about the impact parameter, right? B equals to kz e square cot theta by 2 divided by kinetic energy of the alpha particle. I think remember that. So that also important for 2 marks or problems we can expect on that. Okay. So closest approach we have seen, and as well as impact parameter we have seen. Right. So we'll continue today with Rutherford model of atom. Okay. So Rutherford's atomic model. Today we will see the Rutherford's atomic. Already we have seen in alpha ray experiment what he said. So the continuation of he gave a model. So these are the results of the alpha ray scattering experiment, right? So nothing new, but some new points are there. But the basic thing is nothing but the results of alpha ray scattering experiment. So tell me, what is the results of the alpha ray scattering experiment? With the results, he started doing this model again. He started developing this model, Rutherford's atomic model, right? Now, what are the things we have to consider? So he developed the nucleus, right? So every particle, so every atom, so what it is having, it is a small particle, a core particle we can call, which is called the nucleus. We know that. So points you have to write in the board exams. What you have to write in the first point? So first point is nothing but, so every atom is made up of what? Is made up of the nucleus. So nucleus will be there at the center, and it is of the positive charge, and nucleus contains what? Contains positive charge, and almost 99% of the mass will be located at the center of the atom. Yes or no? So 99% of mass will be located at the center, that is nothing but nucleus, and it is of positive charge, right? That is the first point. First point is, so tiny particles, nucleus will be present, we can write, okay, nucleus will be present, will be in the sense that is future tense, won't be good. Nucleus present at the center of the nucleus, at the center of the atom, at the theory you can study in the different books, story might be same, but screenplay will be different, right? So nucleus present at the center of the atom, and which contains positive charge and 99.9% of mass. Okay, so which contains the positive charge and 99% of mass of what? Of atom. So complete story. We know that all the things what we are studying we know, but we are in 2020 or we are in 1900s. We are in 1900s and we are coming towards the 2020, right? So now assume we are not in 2020 because we know all these things. So, but according to the Rutherford, we have to discuss. In a sense, around 1910 or 1911, he did all these experiments. So we have to go back and we have to study everything, right? So nucleus, we know about the nucleus now, right? Nucleus is of positive charge, right? And 99% of 9% of mass of the atom is what? Is of the nucleus. Next, he said about the radius. The radius of the nucleus is in the order of 10 to the power minus 15 meters, and the radius of the atom, radius of the atom is 10 to the power minus 10 meters. So nucleus occupy very less space in atom. So all the things what he concluded in alpha ray scattering experiment we are discussing here, right? So nucleus occupies very less space in the atom, very less space in the atom. Next, what he said? He said about electrons later on. Yes or no? So what he said about the electrons? Electrons occupy. He said, according to J. Thomson, electron is at rest, but according to Rutherford, electron is rotating. Yes or no? So next he went into the electrons and he said some points about the electrons after that alpha ray scattering experiment, right? So what he said? Electrons will occupy the outer space of atom. Outer space of the atom. In the sense, what inside nucleus is there, we know that. So don't need to by heart anything. We know all the things, but we have to write everything. That is important. Point to point, right? So electrons will occupy the outer space of the atom. Why? Inside nucleus is there. So electrons will revolve in the outer orbits. So that's why he gave the final conclusion that is the outer space of what? Outer space of the atom. Electrons will occupy the outer space of the atom. So next what he gave. Next, okay, electrons occupy the outer space of the atom. Okay, but Rutherford said that the electron is rotating or electron is at rest. Electron is rotating. Rutherford's final conclusion is it will occupy the outer space of the atom and electrons will revolve or electron revolves. Better. Electron revolves. It also occupies better, right? So electron revolves around the nucleus. Around the nucleus in the circular orbits. We know all the things, but we have to write all these things, right? So electrons will revolve around the nucleus in the circular orbits. So these are the different things that what he observed in the alpha ray scattering experiment. So these are the observations again. So with these observations, he continued thinking that, try to understand. So, okay, why electron is revolving around the nucleus? Up to there he came. Okay, so electron is revolving around the nucleus in the circular orbits. But how it will revolve? We are not in 2020. Try to think at that time what he thought. Okay, so revolving around the circular orbits. Okay, so it is revolving around the circular orbits. So how many minimum forces are there? How many minimum forces required? So to revolve an electron, whatever, not only the electron, whatever the particle it may be, should revolve in the circular motion. How many minimum forces required? 2. How many minimum forces required? 2. Okay, he to know that. Okay, 2 forces required in the circular motion. So what are those 2 forces are balancing such that the electron should revolve in the circular motion or in the circular orbits? So that force he gave it as, what are those 2 forces? One is centripetal force. So who will give that necessary centripetal force? Electrostatic force. Try to draw the diagram. What is that electrostatic force? Again, why electrostatic force came here? So nucleus in the center, which is of positive charge, we know, right? And at the outer orbits, electron is revolving. And at the outer orbits, electron is revolving. So assume electron which is revolving in the outer orbits. So this is positive nucleus, right? And this is electron. So this is nucleus and electron. Okay, so in between this electrostatic force will be there. So to revolve, one force is required. What is that? Centripetal force we know. Now who is giving that centripetal force? Centripetal force is provided by the electrostatic force. Okay, so centripetal force to revolve an electron or any particle in the circular motion, centripetal force is required. So who is providing the necessary centripetal force? So necessary centripetal force is provided by electrostatic force. Provided by whom? Provided by electrostatic force. This is the story. So you have to know the story properly. No need to buy it. You can write in the exams after listening this, I think so. So I am trying to do that. Okay. So necessary centripetal force is provided by whom? It's provided by the electrostatic force between nucleus and electron. Between nucleus and electron. So how it is provided? What are the equations and all we will see. So these are the different observations did by the Rutherford, and he gave a model called Rutherford's atomic model. Clear? Can I move forward? Right. Right. So okay. So what is the final point? Centripetal force is provided by whom? Provided by the electrostatic force. So he continued writing like this. So centripetal force provided by the electrostatic force. Right. So what is centripetal force formula? I can write as mv square by r. Right? Try to understand the things. From here we will go into the Rutherford's atomic model and the disadvantages. Then we will start Bohrs model. Okay? So mv square by r is the centripetal force of the electron which is revolving. What is m? Can you understand the terms? What is m? M is mass of the electron and v is velocity of the electron. Can I draw the tangent? Right? So if you draw the tangent, that will give you the velocity of the electron. That will give you what? The velocity of the electron. And this is the radius if you want. So what is r? R is the radius. Right? So we know that mass of the electron, velocity of the electron, and the radius between what and what? Between the nucleus and as well as the charged particle, which is equals to electrostatic force. So electrostatic force between the electron and the nucleus. So tell me the formula K 1 by 4 pi epsilon naught. Right? K Q1 Q2 by r square. Nucleus. What is the charge of the nucleus? Already we discussed in the last classes, right? So what is the charge of the nucleus? Which is Ze plus Ze. We know that, right? So it depends on the atom what we can set the atomic number. So Ze and electron is, we know it is minus C. So electrostatic force K Q2 divided by R square. Separation between them. So only magnitude I am considering. So don't worry, sir. Electron no, so minus C no. So why you didn't write minus? Electrostatic force K Q1 Q2 by R square. Q1 Q2 you have to substitute the magnitudes. You have to substitute only the magnitude. So Z into E divided by R square. So R will be cancelled. So I can write mv square which is equals to KZ E square divided by R. Simple. So how we can write this? Whatever the thing, if it is revolving in the circular motion, whatever the thing, if it is revolving in the circular motion, minimum number of forces 2. Right? So what are those 2? So one is always we know circular motion, centripetal force will be there. So to balance the centripetal force, another force should be there. So if it is, for example, Earth is revolving around the sun. So we will provide the necessary centripetal force, gravitational force. Here, electrostatic force. For example, consider a bike. So if you are rotating around your home, for example, around your home with your bike. So centripetal force will be there. Who will give that? Who will balance that centripetal force? Friction. On the horizontal road, friction should be there. So friction will balance that centripetal force. So here, who will balance that? Electrostatic force. There, gravitational force. Different things will be there, but 2 are mandatory for the circular motion. If only one is there, it will go straight. So it can take the circular motion or it will slips. Okay. So now finally what we got? mv square by r which is equals to kz e square by r got to the Rutherford. Okay, right. So after seeing this, so you two will get an idea. So mv square. Okay, so kinetic energy we can calculate. Yes or no? So divide with half on both sides. So we'll get kinetic energy. If you get kinetic energy, potential energy between these two we can calculate. Then total energy we can calculate. So he thought in that way and he calculated everything. So next topic, what he did, he calculated the kinetic energy of the electron. He calculated the kinetic energy of the electron. What he did? He multiplied with half on both sides. So can I write directly? So half mv square by r, 1 implies. Right? So half mv square by r, which is equals to, sorry, r cancelled. Half mv square, which is equals to this side also half. So it will be kz e square divided by 2 times of r. So this is nothing but kinetic energy. So he gave kinetic energy of the electron is kz e square divided by 2 times of r. Right? So by seeing this equation, he got an idea. Okay, mv square is there, so we can multiply with half on both sides. So we can calculate the kinetic energy of the electron. So he concentrated on energies later. So next, after getting kinetic energy, he is thinking about the potential energy. So calculate. I think in electrostatics we studied potential energy formula. So potential energy, which is equals to K Q1 Q2 divided by R. Now in potential energy, Q1 Q2 you have to substitute with the sign. Why we didn't substitute here with the sign is, this is force. It is having the direction. We can show the direction, electrostatic force, attractive force. But here potential energy is a scalar. So that's why Q1 Q2 we have to substitute with the sign. Try to write that point, try to apply there in electrostatics also, right? So potential energy I can write as K. What is Q1? Positive ZE plus ZE with the sign. But here only magnitudes. Don't be confused. So Q2 minus E divided by R. So what I can write, it is K ZE square divided by R minus. So this will be the potential energy. So kinetic energy he gave, and as well as potential energy he gave. Okay. So kinetic energy, potential energy we know. So can we calculate total energy? He thought like that and he calculated the total energy also. He calculated total energy. So calculate. So what do you mean by total energy? Only electrostatic force is there. So centripetal force is there, that is balancing, right? So only electrostatic force between them. So can I write energy conservation? So he thought to write total energy is nothing but the sum of kinetic energy and as well as potential energy. So total energy I can write as what? Now we know kinetic energy. So can I substitute K Z E square divided by 2R. What is potential energy? Minus K Z E square divided by R. So total energy how much you get? So can I take 2R LCM? So it is kz square minus 2kz square. So it will be minus kz square. So this will be the total energy. Right? So this will be what? This will be the total energy. So how much it is? Minus kz square divided by 2R. Try to see. So all these things comes from a basic idea about the circular motion. Two forces required. How many number of minimum forces required? So 2. So I can write it like this. So later on mv square equals to this. So by seeing this, he calculated kinetic energy. After calculating kinetic energy, potential energy, then total energy. So after getting the value of the total energy, so he thought why minus k? So that we have to discuss, right? So total energy is minus kz square by 2r. What is this minus symbol indicates? That will gives you the stability of the atom. Stable. So always the electron is bound with the nucleus, or I have no relation with the nucleus. I will revolve in some orbits. No, the electron always is bound with what? Bound with the nucleus. So this minus indicates always the electron is bound with the nucleus. Negative sign indicates always the electron is bound with nucleus. We call it as stability also. This minus indicates the stability of the atom. I think if you refer chemistry, I think this will be like this, right? So the negative symbol which indicates the stability of the atom, or the electron is always bound with the nucleus. With respect to the nucleus only it should revolve, not in other orbits, right? Not in other area. So that minus he will get. He got that, right? So total energy is minus k z square divided by 2r. So these are the equations given by the Rutherford. After giving this, try to understand this point. Is that clear? So this is about the Rutherford's atomic model. So he calculated everything about the energy of the electron and all the things. Some changes made by Bohr, okay, but why he made changes we have to understand now. Okay, so he calculated everything, and why Bohr changed all the things. Why Bohr changed all the things is, try to understand. Atom is stable or not? Yes, definitely it is stable. Right. Now, what he said, according to Rutherford, he said that this electron will accelerate around the nucleus. Try to understand the point, very important. Right? So, what according to the Rutherford at that time, what he thought is, okay, a force is there between the nucleus and the electron, so electron will accelerate while revolving. Electron accelerates while revolving, he thought. But a scientist called Maxwell, already I think I said about Maxwell, right? What he did? He was doing some experiments on electromagnetic radiations, right? So Maxwell is a scientist. He is doing some experiments at that time on electromagnetic radiations, like electromagnetic radiations, different wavelengths, different frequencies. On that he is doing some experiments, and he got to know that Rutherford proposed this model. So everything, like a paper, he proposed everything. So now this Maxwell, he applied his concept here. Try to understand the point, important. So now he proposed everything. Okay, what I did is absolutely correct. He proposed a paper in the meeting. Maxwell is there in that meeting. So Maxwell raised his hand, and I want to ask something. He said, and he asked. So I am doing some experiments on electromagnetic radiations. Now, according to me, with my experiments, I can tell whenever an electron is accelerated, it should release some energy. In the sense, some energy should be lost. Right? Understand the point? So what is that? Whenever a charged particle, not only the electron, whenever a charged particle is accelerated, whenever a charged particle, according to us, we write it as electron, but it should be a charged particle, right? So whenever a charged particle is accelerated, it should lose some energy. It lost some energy. It loses some energy or it lost some energy, right? So it loses some energy. Now, if my theory, if I apply here, you are telling the electron is accelerated, okay, very good. That force also, you gave it as electrostatic force, due to, that is providing the centripetal force, okay, it is accelerating, you said. If it accelerates, it will lose some energy. If it loses some energy, the path should be like this, he said, right? So the path should be like this, he said. What is that? See? The path should be, so it is accelerating. If it accelerates, okay? So whenever, visible? Right. So whenever a charged particle, not only the electron, a charged particle is accelerating, it should lose some energy. If it loses some energy, what should happen? What should happen? So the kinetic energy should decrease, loses some energy. So kinetic energy should decrease, and potential energy also some changes should be there. So what will happen? It will come closer to the nucleus, and it will come and finally it will fall on the nucleus. So where is the stability? Sir, where is that stability? Stability is there in the atom, but you are not trying to explain that to us. That is the question of the Maxwell. Actually, it is not happening. Try to understand the point. Actually, it is not happening. But you are not trying to explain to us about that. That is the Maxwell question. And Rutherford failed to explain this. What is that? So, Rutherford failed to explain. Rutherford failed to explain the stability of the atom. The stability of the atom. So it is happening actually. No, it is not happening. But according to the Rutherford, if Maxwell's theory, if we apply here, it should happen. But it is not happening. Atom is stable only. But according to your theory, it shouldn't be stable. But it is stable. Then try to explain about me that, he asked. So he didn't explain about that. So that will be the failure of the Rutherford theory, Rutherford atomic model or theory, right? So what is that? He failed to explain the stability of the atom, right? Try to remember the point. Next. Okay, okay, means that you didn't explain about me that. Then one more doubt. So what is the doubt is, again, electromagnetic radiation. He is doing some experiments, right? So if a charged particle is accelerated, definitely energy should be released, should be lost by the charged particle. Now he is doing some experiment on what energy is lost and that energy is converted to what? What energy is lost, in the sense how much energy is lost and with what particles came out and what is the energy of that particles and what is the frequency of that particles. On that he is doing the experiment. Now one more question he asked. Okay, so you said accelerated, so accelerated in the sense lost in energy will be there. If lost in energy will be there, then with that energy some frequency will come, some wavelength will come. Yes or no? So different wavelengths and different frequencies. If you draw a diagram, we call it as energy spectrum or spectral lines. We'll see in the next topic. We'll see in the next topic. After Bohrs model, we call all those spectral lines, right? So I think different lines will be there. We know series, Lyman series, Bohrs series. I think you studied all the things. It's not new for you, but we'll study everything. So what is the question now? What Maxwell asked to Rutherford? He asked, okay, energy is lost. If energy is lost, what will happen? Some frequency will come out, some wavelength will come out. In the sense, some spectral lines you have to draw. So, what about the spectral lines which is released by the electron? Show me that spectral lines, he asked. No answer. Why? Because he don't know whether the energy is lost or not. But he asked a little beyond about the spectral lines. He don't know about spectral lines only at that time. He don't know in the sense. Maybe he know the topic, but how to relate that topic to here, he don't know about that. He failed to explain about that. What he failed? Rutherford again failed. Rutherford failed to explain about the line spectra or spectrum also we can call plural. So we have written as line spectra. What do you mean by line spectra? In the sense, I have to draw the diagram. I'll draw later. Okay, so different series will be there, different ground state, different orbits you have to consider. From one electron from one state to another state, if it is coming, how much energy it will lost, we have to calculate. All those things, if I draw a diagram, we call it as line spectrum. Okay, we'll study it later, don't worry about this. But try to understand the point. If energy is lost, some energy will come out. So that energy, what it is coming out, we can draw a diagram. That we can call it as line spectrum. Not only energy coming out, if we give some energy to that electron, then electron will jump from one state to another state. It's not new thing, right? If we give some money to you, you will be here or you will jump to another place. Definitely you will go to the other place. The same for electron. If we give some energy, it will go to the higher levels. After completing that money, again they will come back. Right? So all those things you have to draw the diagram. We will see the line spectrum. He didn't explain that. Who is that? Buddha. Clear about the things? After deriving all these things, he proposed that in the proposal, all the different questions arise. These two things he didn't explain, which is raised by the Maxwell. These are the disadvantages of Rutherford's theory. Right. So now, clear about the point? About the Rutherford. This is about complete Rutherford's theory. It's done. So first he started with alpha ray scattering experiment. He gave some basic theories. Then he went to the size of the nucleus. And he discovered nucleus and the impact parameters, scattering angles. Then finally he gave the model. In the model, only two things. He succeeded. Only two things he didn't explain. Remaining everything what he developed is absolutely correct. Only these two things he didn't explain. So to explain this, Bohr came. Right? So next, who continued this experiment? This project continued by Niels Bohr. So now we have to study the Bohr's theory. So he started developing the failures of this model. He took the failures. Okay, why that model is failed? he developed and he gave some theories again. So we have to study about that now. Okay, so we have to study about that. Right. So who came now? Niels Bohr. Okay. Niels Bohr, atomic model. Or first we'll see postulates, and then we'll go into the Bohr's atomic model. Okay. So what he did actually, come back to the story. What are the disadvantages? He took the disadvantages and he is trying to do some experiments, and finally he came to know that electron and the nucleus. Okay, very good. So radius, velocity, and all the same things he considered. This is the radius and this is the velocity. Everything will be same. What the Rutherford discovered, but while thinking about the electrons and the nucleus are very small in nature, right? Very, very small in nature. So now, to Rutherford, what the continuation he said is, Rutherford what he thought is, normally a particle, if we throw with some velocity, kinetic energy will be there, right? And with some height distance, potential energy will be there. Okay, try to come back to the story. Now, Bohr, what he said actually, so general mechanics applying on a particle, or normal particle, will be different to that of subatomic particles. Try to understand the point. So applying kinetic energy, potential energy on the bigger particles, the same way we can apply for subatomic particles also? No. So we have to think little different. So we can't apply the same kinetic energy like normal particles, or the same potential energy like the normal particles. We can't apply that. So these are the subatomic particles. We have to go for the different theories, not the same theory as like we can apply for the bike or the car or any particles. Those are the subatomic, very small. So apply some different theories. He thought, so no. So close everything about the Rutherford's model and keep aside, and we'll start thinking newly about the subatomic particles. So that is the thing. Try to remember that point. Okay. So now what he thought is, so he gave 4 postulates, 4. Right? So according to the different books, I think they will give 2, but according to the major topic of the Bohr, 4 postulates he gave. So we will discuss everything. Try to understand the point. First point is nothing but Rutherford. What he developed? The same. What is that? Electron will revolve around the nucleus in the circular orbits. Yes, that is correct. So that's why he took that first postulate as the Rutherford's model only. What is that? Electrons revolves around the nucleus. Electrons revolves around the nucleus in the circular orbits. So what we studied in Rutherford model, the same he took as his first postulate. Why? Because that is correct. No changes required there. So electrons definitely will revolve around the nucleus in the circular orbits. That is absolutely correct. Now he took that balancing forces also. Centripetal force is balanced by whom or provided by whom? Provided by the electrostatic force. That is also absolutely correct. He took that point also. So if you want, you can include here the first postulate. So I am not including. So if you some questions they will include that model or that point also. That is also correct. So centripetal force is provided by whom? Is provided by the electrostatic force. So both will be same. So we can equate that. Right? That is also correct. He took that model also. What is the first postulate? Electron revolves around the nucleus in the circular orbits, and who will provide the necessary centripetal force? Provided by the electrostatic force. Next postulate, very important. Okay, here you have to understand the things. Electron will revolve in the circular orbits, but Rutherford didn't think about the different terms. Directly he went for kinetic energy, potential energy, and so on. Right? But he has to think the basic thing. What is that? R and particle. Electron is having some mass and is moving with some velocity. Right? So it is moving with some velocity. What about that velocity? Yes, that is important. So according to Rutherford, electron is accelerating. Now according to Bohr, what he said, electron is not accelerating. Electron is moving with some constant speed. Electron is moving with some constant speed. In the sense, the acceleration of the electron is zero. This is very important point. Very important point. Yes, according to Rutherford, it is accelerating. He said some force is there, so it is accelerating. So if it accelerates, Maxwell asked the question that if it is accelerating, energy should lose. That is not happening. But Bohr gave a theory that electron is not accelerating. Electron is revolving around the nucleus with a constant speed where acceleration equals to zero. Now you get it out. Sir, then force is acting no. Yes, sir, centripetal force is acting no. We know in the circular motion 11th we studied centripetal force is required. In the circular motion, centripetal force is definitely required. But that force is responsible to change the direction. Two types of forces will be there. One of those radial force and tangential force. So in the circular motion, who is mandatory? Radial force or tangential force? Radial force is mandatory. Tangential force can be equals to zero also in circular motion. In circular motion, who is mandatory? Radial force is mandatory to change the direction. Tangential force might be there, might not be there. It's not a big problem. If tangential force is zero, tangential acceleration will be zero. If tangential acceleration is zero, then the particle will revolve with the constant speed. This is the story. This is the story given by the Bohr. Right? So, radial acceleration is required. That radial acceleration is provided by whom? Provided by the electrostatic force. That is nothing but the centripetal force provided by the electrostatic force. That centripetal force is nothing but radial force. Right? Now, tangential force is not there, but to Rutherford, he don't know about this. Don't know in the sense he didn't apply that. So if we apply, we get tangential force zero. So tangential acceleration will be zero. Tangential acceleration will be zero. So it will be constant. So this is the thing that we can apply. Right? According to Bohr, what he finally concluded. So electrons will revolve with a constant speed. Right? So this is the thing. So now come back to the second thing. Okay, so an electron revolves around the nucleus, but that we know in the circular orbits. But the angular momentum of the electron, second postulate, very important, right? Angular momentum of electron, which is equals to angular momentum of electron, which is equals to the integral multiple of, if you write, it will be better, statement is equals to the integral multiples of h by 2 pi. Second postulate, try to consider what is that? An electron revolves around the nucleus, that we know. When it is revolving around the nucleus, angular momentum of the electron is equals to the integral multiples of h by 2 pi. What is h? We know Planck's constant 6.6 into 10 to the power minus 34. Don't worry about that. We have to understand about this point now. So why he thought like that? Right? So this day he gave an expression like MPR, which is equals to NH by 2 pi. I think we know about angular momentum. We studied in 11th. So what is angular momentum? Exactly, if I write it as L bar, which is equals to M into R bar cross V bar, or we can write it as M. Can I send inside? So it is R bar cross linear momentum. MB is nothing but what? Linear momentum. So I can write it as R bar cross P bar. R bar cross P bar. So that will be the angular momentum. What is that? L bar, which is equals to R bar cross P bar. Try to understand this point now. What is angular momentum now? What do you mean by angular momentum? What do you mean by angular momentum? It depends on the distance. Try to understand, very important. Very important. It depends on the distance. Distance between the nucleus and the electron. It depends on this and depends on the speed. And depends on the speed and depends on the mass of the charged particle. Now what he finally concluded, why he gave like this is, he did some experiments on the electrons which is of the different orbits, which is there on the different orbits. I think you know about the orbits, right? So of different orbits he considered the electrons and he calculated the radius and he got from this. Try to understand. Now mass is fixed. Try to see what he did, I am telling you. So we can leave from here. Generally the books also they will leave here, but you have to understand what he did. Why he gave like this? What do you mean by quantization? Only charge is quantized, but here I can tell angular momentum is also quantized. Yes or no? So we studied about charges quantized, quantization of charge, Q equals to NE. So now here I will tell angular momentum is also quantized. So how? You have to know the things. Try to come back to the story. So m mass of the electron fixed. And it is moving with a constant speed, that is also fixed, right? And R we can calculate, or after calculating about that particular orbit, R also fixed. Try to understand. R is also fixed, or R we can calculate. Don't worry about that. So if R is fixed, that radius also he added here. He got a value. Try to understand. He again disadvantage is there in this formula. Try to understand. So M is constant, B is constant, R is constant, he got some value. Right. So now after thinking for many years, so this value is equals to what? He thought that. He thought that and he took different formulas like this, and finally this is constant or not? H is constant, 2 is constant, pi is constant. So he equated with h by 2 pi. And whatever he considered, he calculated MVR, that value, and h by 2 pi value, he got the same. So finally he concluded, okay, some relation is there between MVR and h by 2 pi. Now he did for another orbit. He considered another orbit. This radius somehow he calculated, and this speed also somehow he calculated. So mass Vr about that orbit, again speed is constant, and this radius also will be constant. Now this is constant. He calculated some value, and he has that h by 2 pi, right? So he applied them. Oh, he got different value. Definitely he will get different value. Why? Because n he didn't apply. Now second orbit he considered and he multiplied n value with 2. Oh, now again he got the same value. So finally what he concluded is, he concluded the angular momentum. He concluded the angular momentum of the electron should be equals to nh by 2 pi. Now what is the disadvantage here in the formula? Is mathematically he said an h by 2 pi which is equals to MVR, but according to physics he didn't explain. Try to understand the point. He got MVR some values, and after some time he equated with a constant and he got the same, and he proposed the angular momentum which is equals to integral multiples of h by 2 pi. Try to explain me about the physics here. Max we know, so it will be same LHS equals to RHS. So about physics, how you can explain this? Bohr he didn't explain. He didn't explain according to the physics. Now in the later on, de Broglie, again matter waves. As I know, electron is revolving in the sense it lines. As I know, matter waves, complete modern physics topic. Wherever you go, if matter waves or that particle, as I know, particle nature or wave nature, if it is there, de Broglie will come. Why? Because that is his work. As I know, so here electron is there, particle. It is revolving. If electron is moving, it will have the two natures. Particle nature, okay, particle is revolving. While revolving, it should dance. Wave nature. So, de Broglie again came here and he started doing some experiments on the wave nature here. Then, physically, he said how this formula is correct. This formula is absolutely correct. I am not telling formula is wrong. But he said only mathematical way. Who? Bohr. But physically about this formula, who said? De Broglie came and he applied some wave nature here and he tried to explain about this formula according to the physics. That we'll see later how we explain and how this electron will dance there around, we'll see later. That is the story. Okay, come back. So what is the second question? An electron revolves around the nucleus, angular momentum of the electron which is equal to the integral multiple of h by 2 pi. Right. So now In the same postulate, try to understand something. Okay, so now again what he thought Bohr is, okay, so the electron is revolving with the constant speed here. He changed the orbit, velocity changed, radius changed, and everything changed. But what he thought is, okay, this is the first orbit, given the number, okay, this is the second orbit. Now, he tried, many years he tried that the electron, why shouldn't it rotate in 1.5 orbit? And why it won't rotate in 0.5 orbit? Okay, so try to understand this point, important. Okay, so the electron won't revolve in the other orbits. It will be in a fixed orbits, it will revolve. Try to understand this point. Very good. Okay, so electron with the constant speed is revolving. So if the electron leaves one, then definitely it will revolve in two only. And if it leaves two, either it will go to 3 or it will go to 1. In between 1.5, 2.5, all those nonsense won't be there. So why? Because electrons will revolve only in the stable or the stationary orbits. Very important. Electrons revolves only in stable or stationary orbits. Stable or stationary orbits. What do you mean by stable or stationary? Stability. If the electron is revolving at this position, then only stability will be there. Okay? So electron, if it is revolving in n equals to 2, then stability will be there. So it can't revolve from 1.5. It can't revolve at 0.5. So if it loses some energy, directly it jumps back to 1. If it gains energy, it will jumps back to 2. Then it won't revolve in the other orbits which don't have the stability for the electron. Right? So this is the point. The electron revolves only in the stable or the stationary orbits. Now here, what is the final point? Already I said here, angular momentum is conserved. Angular momentum of the electron is quantized. Sorry, not conserved. Sorry, not conserved. Quantized. What do you mean by quantization? Already we studied. What do you mean by quantization? So charge is quantized. We studied Q equals to Ne plus or minus Ne. Yes or no? Plus or minus Ne we studied. What do you mean by this? What do you mean by this? Right answer. N value always it is an integer. So N equals to 1, 2, 3 and so on. In the sense charge, you can tell it has E or 2E or 3E and so on. 1.5E or E by 2. Possibility won't be there. We can't tell Q equals to E by 2. We can tell E by 4. Absolutely wrong. You have to tell. So you are counting the pages. You will count like 1, 2, 3 or it will be like 1.1 page, 1.2 page. Chapter name will be there. Most of you think 1.1 will be there. No, first chapter, first page. Not like that. So if you are counting generally, it will be like 1, 2 and so on. So charge also quantized. So it will be 1. E or 2E or 3. Same here. Come back. N is what orbit number. It will be 1, 2 and so on. So we can tell this angular momentum will be also quantized. We can tell 1.1 h by 2 pi. That is absolutely wrong. Slowly I said. Right? These are the two main important postulates given by the Bohr. What is that? The first one, the same as Rutherford. Don't need to waste time. Second one, about the angular momentum. Trying to say about this. Is that okay? So what is the change made in the Rutherford's model? This is the change. So electron will revolve with a constant speed, not with an acceleration, but force is there. So if force is there, in spite of the force, then you are telling the constant speed, what nonsense is that? That force is required to change the direction of the electron, not for changing the speed of the electron, right? So radial force is there. That radial force is nothing but centripetal force that is provided by the electrostatic force. Tangential force is 0. Next, third postulate. Okay, so we'll go to the third postulate, right? So what is that? What is that? Try to see now. Now it is simple. So we shared about the angular momentum and the electron is revolving. Already we know now the next two postulates. Already I said that. So electron won't electron won't release. So my statement, don't worry about this. First two postulates are important. Electrons won't release energy. Electrons won't release energy while revolving in stable or while revolving in stable or stationary orbits. This we know already, we discussed about this, right? So electrons won't release any energy while it is revolving in stable or stationary orbits in spite of forces there. Yes or no? So in spite of what? Force is acting. So here force is acting or force is not there. Try to understand. Electron is revolving, definitely force is there. That force is responsible for change in the direction, not the change in the speed. So that's why electrons won't release energy, any type of energy while revolving in its stable or the stationary orbits. Energy will release when? That is the first postulate. Electrons releases energy while jumping from or moving. Okay, while jumping from higher energy states to lower energy states. Clear about the point? Energy it can release. Try to understand these 2 points, very important. Electron won't release energy while it is revolving in a particular stable or stationary orbit. So it is revolving in n equals to 1 continuously, it won't release any energy. If the electron is revolving in n equals to 2 continuously, it won't release any energy. But it will release energy when? While jumping from higher energy states to the lower energy states, or higher stability orbits to the lower stability orbits. Right? So, or one more way I can write this. What is that? Electron gains some energy. So it releases some energy while coming back. If it gains some energy, it will lift back to 1 to 2, right? So if electron gains some energy, and then it moves or jumps or lifts, whatever. It moves from lower energy states to higher energy states. Lower energy states to higher energy states. Clear about the point? So these are the 4 postulates. What are those? So first one, it's the same as Rutherford. The second one, we know angular momentum. And the third one, energy it can release definitely. How it will release? See. In the next class, completely we will see about the spectral lines and all. There you can understand how that energy is released, what will happen to that energy, in the form of what it will come out. All those things we can understand, right? So consider nucleus. This is 1, and this is 1, and assume this is 2, right? So if the electron is assume initially electron is at 2, second orbit, and it is trying to come to the first orbit. While coming down, what will happen? It will lose some energy. It is coming from 2 to 1. It is coming from 2 to 1. Definitely it will lose some energy. It loses some energy. How much energy it will lose? Try to write the formula. How much energy it will lose? How much energy it will lose? How much energy it will lose? For every in the next class I will derive the formulas. Try to understand this one. Every particular orbit is having some energy. Here, what is it? If it gains some energy, then it will move. Gain some energy in the sense already it is having some energy here to rotate. Yes. 10.2 electron volts. Yes or no? So if 10.2 electron volts, if it gains, then it will move. Or it will release 10.2 electron volts, then it will come back. 10.2 electron volts is energy required to that electron to jump from n equals to 1 to 2. Sir, how you can tell that? So we'll see in the next class. So we'll get energy formula like minus 13.6 into z square by n square. Right? So Bohr gave the more formulas that everything we have to discuss. Right? So come back to here. So energy in the second orbit is E2, energy in the first orbit is E1. Now the electron is coming from 2 to 1. Then how much energy it will give? E2 minus E1. So how much energy is there in the second orbit minus how much energy should be there in the first orbit. Right? I gave assume 1000 electron volts required for the second orbit. That is 2 more. Okay, try to understand example. 1000 required in the second orbit, 500 required enough in the first orbit. So now while coming down, how much it should release? 500 should release 1000 minus 500. How much? 500 electron volts it should release. That is E2 minus E1. That will be converted to HF. Already this formula we studied in dual nature. Yes or no? E equals to HF or E equals to Hc by lambda. Yes or no? That frequency. So it is coming in the sense that is the radiation according to Maxwell. Yes or no? That is the radiation. If that radiation is having some energy, if energy is there, frequency will be there, we can calculate that frequency. This is the Maxwell thing, what he tried, what he expected from Rutherford. But he didn't care about all these things. But Bohr came and he is trying to explain everything about this. So, about this, we'll write the different diagrams and we'll try to see the line spectra and all in the next class with the formulas of Bohr. Again, he gave the different formulas for again how to calculate the radius of the orbit, how to calculate the velocity of the orbit, what is the kinetic energy required for that electron to move in that orbit, what is the potential energy required to move in the orbit, not same like Rutherford. So little changes are there. Why? Because the formula MVR which is equals to NH by 2 pi we have to include now. Right? So this formula is there. What is that? FC which is equals to FE is there with this first equation we will get. Second equation is what? MVR which is equals to NH by 2 pi. This is the second equation. By solving these two, hint I am giving, you can write. By solving these two, you can calculate the radius, you can calculate the velocity, you can calculate kinetic energy, potential energy, total energy, everything. Then in the next class we will start with this. Then we will continue and we will complete the Bohr's theory in the next class. We will try to complete. Thank you.